What can I say? This is a great honor for me. I'm completely overwhelmed. I think I'd thank everything that's been said. I especially welcome the remarks that Eugenio made about me. I don't deserve any of them, but thank you for saying them in any case. Okay, so what I'm going to do now, I'd like to, first of all, try to get this machine to work. Okay, right, okay. Well, what I want to do really is just go through some highlights of my career and my links with Barcelona. Well, the title that I've chosen there is, I'll explain in a little while. But basically, I want to give a short introduction and background, deal with the first part of my academic career, which was in continuum modeling, plasticity in particular, and then move on into the last 20 years, which has been working on discrete methods on multifracturing solids, and then bringing it all together with work on multiphysics problem. So that's the areas I want to cover. Well, first of all, I should explain the title of the lecture, which was from Binya to Barcelona. So we need to go from Barcelona to Binya to begin with. So this, okay, so we are here in Barcelona, and everybody recognizes London, of course. And then if you go to London, if you decide to go west by about 300 kilometers, you'll come to Swansea. And then if you actually go to Swansea, then about 15 kilometers from Swansea is the village of Binya, where I was born, and where I lived until I was about 18 years old, before I went to university. First of all, I'd like to show you my grandparents. These are I'll use this one. This is my maternal grandparents. This one here is my mother in particular. And these are my paternal grandparents. And the reason I want to show you those pictures is that they couldn't speak English, at all. The only language they could communicate was in Welsh. And in fact, I was brought up in the Welsh language until I was 8 years old. I learned English when I was 8 years old. And I remember telling a director of a chorus Steel this at dinner one night that I learned English when I was 8 years old. He leaned over the table and told me, "Why didn't you finish the course?" So really, I will start with an apology that obviously the language I should be giving this lecture in is a Catalan language, or even if I couldn't do that, I should do it in Spanish, but my Spanish is not good enough for that either, I'm afraid. So I could give the language in Welsh. That would be my preferred language. But then I don't think anybody would understand, although it's very similar to Spanish in roots. So therefore I'm going to force, and as an apology, I'll have to speak in English. So I hope you'll accept that apology. Okay, this is where I was born. This is the house where I was born was there. And this is the first school that I went to, Binya School, which has now been demolished, actually. So what I will briefly give you my education. That first of all, I went to Swansea University, which, as I said, 15 kilometers away from where I was born. We've seen pictures of the campus already. And it was a very fortunate choice that I made, because a year after I went there, Oleg Sienkiewicz decided to come to Swansea. He probably had heard that I was studying there and decided to come and join me. And this was the best thing that I ever did, that I got my first degree there and my master's degree there. And then I told Oleg I'd like to go to the States to do my PhD. And he arranged for me to go to Northwestern. And this was where he'd come from. He'd been there from 1956 till 61. And so I went to Northwestern to do my PhD. And this is myself and my wife Janet. And this is the president of Northwestern at that time, J. Roscoe Miller. Then, after I finished my PhD, I'd gone there as an immigrant, and I had a green card. And for some reason, as soon as I finished my degree, I got my degree on a Tuesday, and on a Friday, I got an invitation to go for a medical for the US Army. And for some reason, they thought that as an immigrant that I should actually come and join them in Vietnam. Anyway, a week later, I arrived back in Swansea. And I went to see Oleg, and And I said, I promised Oleg that I will take a post in Swansea for 1 year only while I looked around. But then I got seduced by the finite element method and also the way that Oleg ran the department. That first of all, it was a case where administration was negligible. He didn't believe in administration. Teaching was efficiently dispatched, but research was to be carried out at every opportunity. And also we had so many visitors at any given time. There would be at least 6 people from all parts of the world, which are senior academic people, all visiting Swansea. And it was an excellent place to carry out research. So this is the historical background of the finite element. I just put that up there. This shows the development of the finite element method from the basically the mid-50s onwards, going through from the first papers on solid mechanics and then moving to nonlinear problems of fluid mechanics, parallel processing, discrete elements, etc. And so essentially I came into the field at about 1967 when I returned to Swansea after finishing my PhD. And then the connection with Barcelona started shortly afterwards. That in 1976, Eugenio decided to come to Swansea to do a PhD with Oleg Sienkiewicz in metal forming and plasticity. And as you can see, he's very successful. He finished 2 years later, and that is Eugenio receiving his PhD in 1978. And from that time onward, there's been a continued cooperation between Swansea and Barcelona. As Eugenio already said, in 1979, he invited myself and Ernie Hinton to come and teach a course here, and then the cooperation has started from that time. And in fact, the cooperation still goes on to this day, because it turns out that the head of the College of Engineering at Swansea is in fact Javier Bonnet, who is actually a UPC graduate. So if actually, as well as actually cooperating with Barcelona, we actually managed to steal one of your most important people. Continuum modeling, let me just show 1 or 2 examples of continuum modeling, particularly plasticity. This is a problem that I solved in 1970. It's a highly cited paper, and it's a case of a bending of a notched beam. And what happened is that we did a numerical simulation that tried to compare it with the exact theory. And what you find is that that's the mesh I'm showing there. But if you compare the solution, this is the distance below the notch root on that axis, which is this distance here. And if you compare the solutions, the Henke solution was supposed to be the exact solution. And what you find, the numerical solution agrees with the Henke solution up to a certain point, and then after that, the solutions diverge. And what happened is that the assumptions made in the exact solution were incorrect. That the basic assumption that you make in the Henke solution is that the through thickness stress, the sigma ZZ, which is this one here, the assumption is made that this stress is always intermediate. It's not neither the maximum, it's not the minimum. And what you find is, as long as that condition is satisfied, that the 2 solutions are in agreement. And as soon as sigma ZZ becomes the minimum stress, then the condition of the theoretical solution is violated and the 2 solutions diverge. This is one example of numerical methods actually providing a role in proving a theory incorrect, or actually allowing us to actually improve the state of knowledge just by using numerical methods. Also, from that time onward, we worked a lot on finite strain plasticity with contributions in material nonlinearity, large deformations, adaptive mesh refinement, contact modeling, and so on. And through that, we had a long collaboration with Barcelona. We did many European projects together. We did many in metal forming. And these are some examples of the kind of thing that you can do. This is a case of a can which is vacuum loaded, and you can actually model it. And on the left-hand side, you have the actual experiment. This is a case of forming a plastic container, and sorry, back. My mouse is not working well. This is a case where you have to use adaptive mesh refinement. This is another example where contact is important. This is the modeling of hair. These are 10,000 individual hairs, and there's contact, which is modified by the presence of materials like shampoos. This is another problem of making of a soap bar, where the soap is injected, and then you find that it actually just fills the mold, but there's a lot of self-contact between between parts of the soap, and therefore, when you start using it, you find that the bar breaks down. So the solution to that problem is simple: that you actually just inject the soap and remove the injector, and then you find that in this case, then you end up with a bar with no defects in. And these kind of problems, we worked together with UPC at that time. Lots of problems in the forming industry, and we were very successful. Another one is oblique impact. This is a case of a tungsten rod penetrating a plate, a steel plate, and you can see there's lots of large deformation there. There's fracture because the material has to penetrate the plate, and also mesh adaptivity plays a very important role. And this is the start of the move towards discrete behavior. This is another example. This is a case in the oil industry trying to replicate what happens in geological depositions. This is an experiment carried out at Imperial College by Maclay. And the experiment is that we have a sheet of rubber, and then we draw that sheet of rubber and then keep on adding layers of sand. And what you see here is that you have a lot of shear bands developing, multiple shear bands developing. And so the material starts not to really behave like a continuum. And this is a comparison of the numerical solution with the experimental solution. And what you find is that you actually replicate the essential features of the problem, that you have. You see the shear bands that you develop there are very similar to the shear bands that you see. Gosh, this mouse is good. That the shear bands, I give up, right? That the shear bands for the experimental side are in agreement with what you see numerically, and what we have here is discrete behavior beginning to take over. So the second part of my career, from the 1990s onwards, I started looking at discrete phenomena. And the first thing I did there was a discrete element method. And discrete elements are really nothing different to finite elements. The only thing is that they are not connected. There's no nodal connection. And the only way they make contact is by some interaction laws or some adhesive laws between neighboring elements. And the biggest problem in discrete elements is how do you detect large number of objects? Because typically you may have over 1 million or 10 million objects. They are different shapes. And also the event goes on for a long time, so that you may have to do this for, say, about 1 million time steps. So the procedure by which you monitor contact is the crucial one in discrete element methods. And the global contact search, as it's called, usually involves bounding each element with a simple geometry, in which case a cube, so you can define the geometry of the element by its lower coordinate and its upper coordinate. And then you can actually develop algorithms to decide which of these boxes overlap. And there's two solution procedures. One is a log-based, tree-based scheme, which is of complexity n log n. But the better methods now are cell-based methods, which are linear complexity. In other words, if you double the number of objects, you double the computation time. Eugenia's already shown you this. I'll play it again, but the only thing I want to point out is there are 500,000 particles in that model, and throughout that history, that you have to decide which particle is in contact with what other particle. So you can see the complexity of contact algorithms. But these are now just particles. Now, the next thing we want to do is to take a continuum and fracture it. So we want to look at multi-fracturing solids. And the first thing I would ask is fracture important? Well, if you look at this problem, okay, so he fractures his bat, so he gets another bat, he fractures that one as well, and then he takes another bat. And so basically, as long as somebody's going to give him a supply of bats, then fracture is not important. But on the other hand, if I show you this problem, this is an aerobatic pilot, is flying, and he's going to do some aerobatics. Now, it's a very bad picture. It's an amateur footage. And he starts going into a roll. He goes into a roll now, and a wing falls off. Two things that happen now. First of all, aerobatic pilots don't have parachutes. And secondly, aircraft don't fly very well on one wing. So the question is now, I think the pilot is probably thinking, yes, a fracture really is important at this stage. But it turns out, that all is not lost. So that you think that he does actually manage to regain the situation just like this. And this shows that there is actually a pilot in there. And this shows the reaction of this guy. So I think we can conclude that in some situations fracture is important and the understanding of fracture is important. Oops. Oh. Right. So we decide that we're going to model fracture. Okay, so the approach we've taken is to start from a continuum and then change it into a discontinuum. So first of all, we start with a continuum where we model fracture on a rotating crack basis. And then on the compression side, we use some failure surface. It could be anything. We're using what's called a SR3 model, but it could be anything. It could be Moore Coulomb, Drucker-Prager, or so on. And then as soon as on a continuum basis that you detect fracture, then we actually insert a fracture on a nodal point basis. So we go to every nodal point for where the region surrounding it is fractured. We put in the fracture surface whose direction is given by the conditions of the surrounding elements, and that means you introduce another node here. So therefore, we end up having to locally remesh the material to accommodate the fracture. Validation, because I also showed you that problem with the shear bands. Validation for these nonlinear problems are highly important because you very rarely have any sort of theoretical solution. So you always need validation with experiments. And this is a case of a validation of that technology which I showed, insertion of discrete fractures. This is a case what is called the standard problem is bore-hole breakout, that you can actually take a piece of material, drill a hole through the center, and then apply a series of, I've got to mind myself what this is. Oh, sorry, we get back. And then you can apply a series of pressures on it. And for our model, this right-hand side shows that the only material parameters that you need for these problems are the tensile strength, the fracture energy release rate, compressive strength, and also the parameters that you get from a hydrostatic stress, the cohesion, friction angle, and the dilation angle. And what you find is that just by changing the material properties, you should be able to get different types of behavior. For example, for the material properties for granite, which are the ones given there, then experiment shows that we have fractures occurring at 3 o'clock and 9 o'clock, and that the fractures are in a vertical direction mostly. This is just a blow-up of that region there. You see the fractures are mostly vertical, and you produce the same kind of behavior in the numerical model. On the other hand, if I just change the material properties to limestone, then the behavior is completely different. Nothing's working here. Oh, I get it now. Right. Okay, so that in the experiment you find that the fractures are discrete, and then in the numerical model you pick up the same kind of behavior. So you go from this kind of behavior to this kind of behavior, and the only thing I've only done there is change the material properties. So this shows that the model that we're using is correct, is validated. This is so-called end-on impact test, which is a silicon carbide ceramic. This is a tungsten impactor, steel plate. And then if you impact it, you find that you develop fracture patterns like that. And the reason I want to show this is that I show you that you need to continually remesh this problem. As you go from 0.9 microseconds to 6.9, you see the fractures are developing, and that means we've got to continually update the mesh so that we can actually model the individual fractures. So we go from a very coarse mesh to a very fine mesh, and this is done by automatic remeshing. Sure, you can do the same thing in 3D. This is the so-called Sugano test. It's a reinforced concrete plate. It's impacted by these three masses, which are meant to represent a jet engine, and on a spring, which is meant to represent the casing of the jet engine. And essentially, what you can model is this kind of behavior, that you get, first of all, a compression wave is just reflected as a tensile wave, and then this causes a fracture around here, and then you get these series of rings that take fracture rings that occur. Also, we have steel reinforcement in there. So this bottom picture here shows the deformation of the steel, which is represented as elastoplastic bars. Right. I should say as well that a lot of the problems I'm solving are rock, and rock is not a homogeneous material. Basically, rock is made up of things what is called persistent joints and faults, which are just major faults in the rock. Then in between that, you have what is called subfabric, which are smaller fractures, and then between the smaller fractures, you have intact rock. So the approach that we take is to actually put in the main fractures into the model, and then in between those fractures, we create a numerical triaxial cell, where between the fractures we put a smaller veins in, we take intact rock data from a triaxial test, and then we perform an analysis of that, numerical analysis, and obtain the parameters that you need for the soft rock model, or the Mohr-Coulomb Kaptur-Prager model, or whatever you're using. So it's a multi-scale approach in that the material in between the main fractures, you have to build up the parameters from a numerical triaxial test. This shows what we're doing there. This is just a block of rock, and we're putting in the main fractures directly into the model, and now we're going to excavate these in a series of steps, 12 steps. And what you see, you get the classical slip line failure. You also get a series of fractures occurring throughout. You get fracture occurring in the shear band here and also on the surface. So we have a mixture there of continuum behavior and discontinuum behavior. I lost my mouse again. Right. Okay, now that is simple. This is fracturing material there, but with one medium. Now, what we want to do is couple this fracturing behavior with other kind of phenomena. And this one is with gas flow. That we're looking at how rock fractures with under explosive loading. I've got to put a few equations in, otherwise it's not a technical lecture. Those are just the equations of gas flow. And what we have here are two problems. We have the fracturing material, which we treat as a Lagrangian mesh, and then we have a background mesh on top of that, which is a fixed mesh. It's a Eulerian grid, and we've got to solve the gas equations on the Eulerian grid. And we pass information between the two grids. We send from the rock fracture model that we obtain the porosities in the rock, which we then use in the gas flow model to determine the pressures. And these are two solutions here. This is a case of what is called HPE benchmark, high performance explosive benchmark test. And what we have here, we'll detonate explosive in that central hole. And then what we find is if the boundaries are free, that we get a compression wave, which is reflected back as a tensile wave, causing tensile cracks around the boundary. On the other hand, if you have a non-reflecting boundary, then if you allow the wave to pass through, then you simply just get the fractures going out and nothing getting reflected at the boundary. On that top of the right there, it shows you also that the materials are highly strain rate dependent. That as you increase the strain rate, the tensile strength changes by at least an order of magnitude. Some more serious problems. This is a case of Bairn's benchmark test, where there are 5 holes here, and each contains explosive, and you detonate them with a 10 millisecond delay, and then you turn that continuum into a discontinuum. And the reason why that's called a benchmark test is that the particle size distribution from the simulation is compared with what actually happened at Bairn's. And the particle size distribution, it turns out, are remarkably similar. This is another one designing, this other one here is designing a sequence of blasting for a coal mine. And the idea is there you want to detect what is the particle size distribution and also what is the extent of the throw of the material. Right. Another problem is vacuum dredging. And this is another coupled problem between particles and, in this case, fluid, which is water. Not many people know that 50% of the world's diamonds are not produced by mining. They're actually produced by harvesting rock from the seabed. The diamond-bearing rock gets washed out of the Orange River into Namibia, into the Atlantic Ocean. And then they collect the rock. It's about 100 meters below the surface. You've got rock particle sizes up to about 1 meter in diameter. And what they do, they have this gadget here, NAMSOL 2, which is an automatic robot which goes along the seabed and actually sucks up the rock. And so really, it's like an underwater vacuum cleaner. But it doesn't work very well, so we've been trying to model this behavior. And what behavior we've been using is using a lattice-Boltzmann approach to model the water and a discrete element approach for the rock. Now, I don't have time to talk about the lattice-Boltzmann method other than to say it couples well with discrete elements because they're both explicit type techniques and they fit well into the same kind of code. I'm not going to say anything. Basically, the grid, what you do is divide the region into a grid, and at each point there, in 2 here, you actually define the density distribution functions. From those, you can get to recover the velocity and the pressure. And then you do a streaming operation where you move everything to neighboring nodes and then gather information to do an equilibrium balance. But the biggest problem that we have is that we have particles which also sit in this water. And these particles are large. They're much larger than the grid spacing for the fluid analysis. So therefore, you have to enforce the boundary conditions of fluid onto the particle. Best way to do it is the so-called immersed moving boundary, which is second order accurate. You have to introduce an extra operator, which is a collision operator, omega. And what it means is that the equations on the bottom become modified. I lost my mouse. God, that's come back now. Right. So the equations for the lattice-Boltzmann equation become modified by the introduction of this extra term, which is the collision operator. You also need a weighting parameter B, which is really just the area of the area surrounding a node, how much of it is solid and how much of it is fluid. So the kind of thing you can do is the following. This is vacuum dredging. These are particles. They're polygonal particles, different shapes, different sizes. And what we're going to do is just suck these particles up there. Also, you will see that the Reynolds number for this problem is 70,000, so I haven't told you, we also have to introduce turbulence model into the fluid model. We use this Smogorinsky approach. So essentially, we can actually couple this time particles with water. And I'll do one more for you. This is quite new work we've been doing on magnetorheological fluids, which are micro-nano-sized particles embedded in the fluid. And what you're trying to do is actually modify the property of this mixture by applying a magnetic field. And the applications are many. There's applications in the field of automotive, clutch material, shock absorbers, and so on, but also in biomedical, too, in the design of robot blood and mechanical blood. NASA is very interested in that. And also drug delivery, that you can actually try to steer your drug or deposit your drugs where they are actually needed. From a numerical point of view, what you have to do is to model the chain formation and how that affects the rheological properties. So I'll only concentrate on this part here, because we've looked at the hydrodynamic forces come from the lattice-Boltzmann and the discrete element method, as do the contact, as do the gravity. Now, the only new thing that's in there are the magnetic forces, the forces on the particle produced by the magnetic field. And that will come from Maxwell's equations. You can get Maxwell's equation here, which really is in terms of the magnetic field intensity. And then you can compute the force on the particle by simply integrating the Maxwell stress tensor around the boundary, and the Maxwell stress tensor is that bottom box there, which again is given in terms of the magnetic field intensity. So we can actually compute the forces on the particle produced by the magnetic field. So if we take an RVE of that, what we have here is random distributed particles subjected to a vertical magnetic field. And what you find is that just by applying the magnetic field, that the particles arrange themselves into chains. And this one is just looking at the top of the same thing. So the next question is, having formed these chains, how do they actually change the viscosity of the material? So we form these chains, and then if you look at it, if you go then and apply a horizontal velocity to the top surface, then we can compute the force on the top surface, and from the force then we can actually compute the apparent viscosity. So what we have in the bottom picture there is, as you change the shear rate, because depending on the velocity you apply at the top, you can change the shear rate, and you find that as you increase the magnetic field intensity, that you can actually increase the viscosity. And this change is instantaneous, so you can actually control the property of this magnetorheological material. Right, that's enough of that. Let's get out of there. It's going backwards, isn't it? God. I'm sorry, this is not obeying me. Okay, right. As Henry mentioned, a lot of the work we do involves parallel processing. The problems get rather big. So I've been working on parallel processing for the last probably 30 years or so. And the biggest challenge is, as far as particles and multifracturing solids are concerned, is that the topology is continually changing. As you're fracturing materials, you get more particles, and therefore if you do a domain domain decomposition, that is continually changing. So basically that we have to have dynamic load balancing. You can't just actually do a load balancing at the beginning of the problem. You continually change the load balancing. And this also means, if you're using distributed memory, that you have to look at incremental data migration. Hardware choices are shared distributed memory, mostly distributed memory these days. Also, we use a combination of multi-core processors and also GPU accelerators. If you look at the world's best machines, this is rather out of date, I'm afraid, but up till last year, the second fastest machine in the world was the Cray Jaguar, and that is at a peak performance of 1.7 petaflops. And then that was overtaken by the Chinese machine, TN1A, which was 2.5 petaflops. But this is May last year, and since then the Japanese K computer at the Riken Institute has come along, and that operates at about, peaks at about 10 petaflops. But the reason I wanted to show those two was this shows how inexpensive parallel processing has become. That if you start off with the CLAT2, which was the first machine that delivered a gigaflop for $1,000. Since then, the Jaguar will give you a gigaflop for $59 and the TN1A for $35. And so basically, the unit cost of computing is reducing all the time. But we should also compare that with the computations of Richardson, who actually solved the Aswan Dam in 1910. And he had computers as well, but in this case, the computers were students from the local high school. And he actually paid them n over 18 pence per node, where n was the number of digits of precision. And he had also the luxury of actually refusing to pay if the computations were incorrect. But now, these days, we're moving towards exaflop, 10 to the power 18 floating point operations per second. And DARPA, the Defense Advanced Research Project Agency in the States, have already set up contracts with MIT and Sandia, and the first prototype should appear in about 2018, and that'll be built in Sandia. And the main challenge is that you have to reduce power reduction, that in order to, you need to reduce power reduction by at least 2 orders of magnitude, hopefully 3, in order to get something that works. And the other thing that people don't tell you is that data handling, because you have enormous amounts of data being generated, being input and output from these systems, and they are going to give us increasing challenges. But let me give you a warning to finish. I'll talk to you about the rump problem. This is Siegfried Rump, who was working at that time for IBM in Berlin, and that's the publication. And he said, if you take that function, it's quite a simple function of x and y is to the power 6, and there's only a linear division in y, so it's not a very nasty function. He said, compute that function for x, that value, and y equal to that value. So you can put that into your computer, and if you use single precision, you'll get that answer. If you use double precision, you get a few more digits at the end. Or if you really want to go crazy, you can use extended precision, which again gives you the same solution with a few more digits. Now, the only problem is that the correct answer is minus 0.82. So the computer can't even get the sign right. And the reason you have to use what I call mathematically branch and bound methods in order to get the correct solution. So I put that as a message, that high-performance computing is not about getting the wrong answer fast. And this is probably stated by Richard Hamming. He's one of the guys who worked on the Manhattan Project. He's a mathematician in the States. And he said the purpose of computing, we should all remember this, is insight, not numbers. Okay, we've mentioned Rockfield. It's another part of my entrepreneurial activities. This is Rockfield's building. We built it ourselves. Well, we built half of it ourselves. We collaborated with another company to pay for the other half. Rockfield, we've got the top floor there. We rent the other part out. Also, we have a place in Australia on the Barrier Reef in Townsville. There's 10 people working there. And what you can see there is roughly the same amount of blue sky in Swansea as there is on the Barrier Reef. Also, I feel obliged to go there in January very often for marketing meetings. And this is us on the Barrier Reef actually doing some fishing. Now, the important things in life to me, first thing is my aircraft, Victor Charlie. It's a Cessna 172 Skyhawk. And my most important qualifications are on the right-hand side, my pilot's license, my instrument flying license, my night flying license, and my radio license. So that's by far the most important thing. And the other thing is that I played rugby football for 20 years. I gave up when I was 35. And this is just one picture of us actually playing. Then we got the funded element community in action. Everywhere you go, you see that funded element people are always enjoying themselves and having a good time. I should also say that the funded element community is a very pleasant community that everybody gets on with everyone else. There are not many people who are very obnoxious or anything. I think, you know, that by and large, everyone in the funded element business gets on with everyone else. It's very good. Eugenio has actually highlighted these, so I won't go through that at all. Also, I won't really mention much about the Swansea UPC connection because Eugenio has covered that very well. As I said, in 1979, we started our courses in the old building, which is now where the rector is housed, and then later on we moved on to the new Campus Norte of UPC. And also, Eugenio has talked about the different conferences that we organized over the time. I'll finish off really with the quote in the PTAC report, because we've all been working for the last 30 years on computational modeling. And it's nice to know that the importance of computational modeling is becoming recognized. The PTAC report, the President's Information Technology Advisory Committee identified the computational modeling as the third pillar of scientific progress. That is equally as important as theory and physical experimentation. And it concludes that the most challenging problems in this century will be conquered by people who have access to computational technology. Right, I shall finish off. This is a famous painting in Wales. I started in Wales and I finish in Wales. This is a famous painting. It's probably in 50% of the houses in Wales. And what the first thing you notice, everybody looks very miserable. You see, this guy's got his head in his hands here. I mean, she doesn't look very happy at all. And if you look at it closely, you'll see she's very unhappy because she's got her mouth is down. She has lots of lines in her face. And I think if this painting was repainted now in this year, 2012, she would now have a smile on her face. A lot of her wrinkles will have disappeared. And the reason for that is obvious, that now she has access to computational modeling.